Thank you. Okay, welcome to our talk. Thank you for coming. We appreciate you spend your after lunch time with us. So, my name is Natalia, and I work in Microsoft.
And my name is Oleksandra, and I also work at Microsoft.
Yeah, we both work with data science. So, data science and machine learning are really fast progressing fields, and a lot of things happening, and a lot of new things are getting out every single day. Well, not as many new things as like new JavaScript framework every day, but a lot of things every day. So it's very challenging to keep up, and that's why we decided to make this talk in order to share what has happened in the last years and what are promising new directions. So who in this audience are actually working with data science or machine learning? Please raise your hands. Good. Who have heard about machine learning? Something. Perfect. Perfect audience. Thank you very much. So the list of topics we're going to cover, of course, is very subjective, so you should not hold it against us. That's what we think is the most interesting and promising. But we are not going to talk about what's supervised or unsupervised learning. I hope you already know that. We are not going to make a house price prediction. I think you have seen it already. We are not going to explain how neural network works. That's also not this talk. What we're going to talk is on that screen. And we're going to talk about what's responsible AI, what's machine learning, and what's fairness. We talk about model interpretability, automated machine learning, transfer learning, what's adversarial networks, deep reinforcement learning, and causal learning. Given it's Friday afternoon, and it's again after lunch, we try to make it easier, so there's not going to be a single formula on the screen, so just relax about that. And if this list doesn't make you curious, it's absolutely fine if you just step up and leave now. We will not hold you against you. No? Thank you. If you choose to stay, since you're choosing to stay, that was your goodwill, people. We didn't force you. It's the first time we run this talk. So we would really appreciate your feedback. So if you have any feedback after that, please come and talk to us. Well, with mandatory pre-word being over, let's get started. Buckle up.
So before I left my hometown to study at university, for some quite long period of time, I used to live with my grandparents. And my grandfather had an enormous collection of science fiction books. And my sister and I would spend sometimes fighting over some of those books. And I remember vividly, I couldn't quite understand sometimes what those books were about. What I soon realized, however, that those books were not about science per se, or future technology, or some adventures in space. It was just a setting. They went past and beyond those topics and raised eternal questions, so to say, like what defines our humanity, what defines mortality. Is there a limit to our abilities, to what we can explore and perceive? And if someone can feel and understand reality and act in the same way like we do, does that make them human? And yeah, by the way, I watch a lot of movies. Please raise your hands. How many of you have heard of Isaac Asimov?
Wow, really
Cool.
good audience.
Yeah. The science fiction author Isaac Asimov envisioned a world where robots would act like servants and would need to be programmed specifically to not harm people. Thus, in 1942, he created the famous 3 laws of robotics to protect humans from dangerous interactions with robots. 77 years later, that's not fiction anymore. That's becoming our reality. Today, AI is not as good as someone hope and not as bad as others fear, but humanity is accelerating into a future that very few can predict. We have people like Elon Musk saying that AI will eat us for breakfast. Stephen Hawking said it was the biggest threat to humanity. Meanwhile, actual AI researchers seem to be amused by such statements. For instance, one of the top AI leaders, Andrew Yang, said that fearing the rise of killer robots is like worrying about overpopulation on Mars. But despite what we might be hearing about artificial intelligence, machines still can't think like a human. However, in the last few years, they have become capable of learning. And suddenly, our devices have opened, so to say, their eyes and ears, and cars have taken the wheel. Such technologies seem to improve our lives, at least by making it more interactive. I don't think anyone would deny that it's always nice to have someone to talk to. However, as anything, AI may have the opposite impact on our lives because of such well-known issues like loss of privacy and control. One obvious question, like how many of you use Google?
Raise your hands, please. Google
Yeah,
users?
pretty much everyone, of course.
Okay. Keep your hands up. Please keep your hands up.
But how many of you have turned the tracking off? Like, as you can see, that's a screenshot from my account.
Lower your hands
actually.
if you actually turn the tracking off. And those who didn't turn the tracking off, keep your hands up. Yeah.
And how many of you believe that Google has actually turned the tracking off? Conspiracy
Somebody?
theory.
Who
But
believes in that?
I mean, we can only believe, right? How can we possibly check? So that's just one of the illustration of potential issues like loss of privacy. Another example. I'd like you to imagine you come to a restaurant to order some nice big chocolate cake. You have been wanting it all week. Maybe not many of you can relate because not all of you are sweet tooth like me, but anyway, some AI assistant decides that you've had enough of sugar for the week and they bring you some salad instead. Yeah, very plausible situation. I mean, I might be exaggerating here a little bit, but I don't think, honestly, anyone would like to live in a world where your decisions are overruled or undermined by AI. So, although AI might not be at human-level intelligence yet, it will be one day. Today, we deal with narrow AI, meaning that it can solve just one particular task, like playing Go or translating a piece of text. What some researchers are actually aiming for is general AI that can solve any general task. It is essential to understand that the progress in machine learning is exponential, meaning that it can start off rather slowly, but there is a certain point where it speeds up dramatically. The difference between narrow AI and general AI can be extremely large, but the difference between general AI and super AI can be much smaller. Once we have general AI that can function like a human being, most probably it won't stop there. It will keep going and it will keep getting so advanced that there will be extreme explosion of new knowledge and information. Some of it might not even be understandable to us. This is known as the technological singularity. And then there will be a point of no return. Dramatic. That's why it is very crucial to establish the policies for responsible AI early on to ensure its ethical and sustainable development for humanity. That's why in December last year, Canada is ahead of the world, University of Montreal published the Declaration for Responsible AI. And I'd like to share the key point from it which is surprise, responsibility. Humans should be the ultimate decision makers. And my sister likes to joke that, Sasha, make sure you create the turn off button with the robot, because she doesn't know actually what I work on. So anyway, to ensure that human rights are not violated by AI decisions, we first need to determine at which stage in the algorithm it becomes possible, which brings us to the next hot topic in machine learning bias. Machine learning models, by default, are not objective because data and features used for training them are created and gathered by us, people. And want it or not, we are all biased by our experience and society. For instance, the famous word-to-vec algorithm revealed many biases in the human language. The algorithm learned semantic relationships between words in English language without any prior knowledge of the language itself. It represented how different words related to each other in various contexts. A famous example is a man relates to a king as a woman to a queen. However, as you can see, the algorithm also showed the implicit sexism in the language. For instance, it showed that a man relates to a computer programmer as a woman to a homemaker.
That's probably a less popular example.
Maybe. Biases are so hardwired into our lives that it doesn't even take machine learning to experience them. For instance, have you noticed that most voice assistants are set to young female voices by default? Why is that? It turns out that both women and men prefer female voices because they sound warmer, and so both men and women are more likely to buy such products. However, according to the recent report by the United Nations, it only reinforces the existing prejudice that women are always eager to help, ready to please, without any personal agenda. Another study now at Stanford University showed that people actually prefer female authoritative voices in the situations.
Male authoritative voices.
Oh, sorry. Freudian slip. But yeah, male authoritative voices in the situations where they need advice or directions. For instance, back in the 90s, BMW had to recall their entire GPS system just because male German drivers were refusing to take directions from a female voice. So, let's say an engineer is building a model to predict aggressiveness in dogs. He truly believes that a particular breed of dog is very aggressive, maybe because of some unpleasant encounter in his past. So when the resulting model suddenly predicts this is not the case, the engineer keeps retraining the model until it produces the result that confirms his beliefs. This is known as the experimenter's bias, a form of confirmation bias in which an experimenter keeps retraining the model until some pre-existing hypothesis is confirmed. So this is just some examples and high-level overview. And now that we actually are aware of human biases, how do we actually ensure fairness in a machine-learned model? So one approach has been to post-process the output produced by a potentially unfair classifier. So you would first train the model as usual and then recalibrate the output to enforce fairness. Although this approach has been good in decreasing the bias of the classifier, having it as a separate step after training introduced a questionable trade-off between fairness and accuracy, because then you had to essentially do the trade-off and balance those two things. Another approach has been to remove features corresponding to the protected groups, like ethnicity, gender, or age. Let's say we want to make sure that a resume isn't ranked lower just because it's coming from a female. Please raise your hand if you think that removing gender as feature would help. Now is a good time to raise a hand. Or anyway, yeah, good catch.
Good audience.
Yes. The thing is that, again, research showed that data can be biased in very complex ways, potentially undetectable for a human. And I thought of maybe somewhat intuitive example. Let's say even if we removed gender's feature from whatever data set of resumes, we might still infer that some of them are coming from female, some of them are coming from male. Let's say someone went to the army or had some gaps because of maternity leave. So things like that. So we can still have biased data set. So actually, reducing machine learning bias is an active area of research. And Google has recently published a paper where they suggested a novel technique to train algorithms fairly. And the key idea behind their paper is that behind any unfair or biased data set, there is a hidden unbiased data set. And so they try to reweight the original data set to feed that theoretical unbiased data set, and only then they use that data as a training data. So maybe you've heard of a joke that if you torture your data long enough, it will confess to anything you'd like, meaning that statistics can be largely manipulated to enforce any conclusion. And machine learning is vastly based on statistics. And many industries, such as banking, insurance, hiring, can use machine learning in their decision-making process. And if those decisions are based on biased predictions, it will be, yeah, so to say, detrimental to the end user, because it will just contribute to more unfairness in our lives, which is already a bit unfair to me. So this becomes crucial. The machine learning reduction and ensuring fairness in machine learning process, which brings us to the next hot topic, model interpretability.
Yep, so model interpretability, and what is it, and why do we actually talk about it at all? Well, we talk about bias, we understand that. What's model interpretability? Machine learning has great potential. I think it's out of questions. It can improve a lot of our systems. It can be very helpful in research. There is only one problem. Machines usually do not explain why they take a decision or why they made such prediction. They just say, it's so. And that is actually a barrier towards bigger adoption of machine learning in the industries. So, because regardless of what is the end product we're building, user will always prefer the model which can be validated and she can understand. First of all, if we can validate, we can see, okay, this is kind of fine. If we understand what's inside, we can improve it. Because who wants to improve something? You have no idea what's inside. It's pretty much like blind game. So, and also we want to build models we trust. And that actually means build something which we can incorporate into our mental way of processing. So in some domains, machine learning and interpretability or understanding machine learning models is desirable, but some domains directly require it to be explained. So why this decision was taken. For example, in finances, a system has to pass audit process which would prove the decision taken was not discriminatory in any kind of way and was not breaking any laws. Let's say you go to doctor and machine learning algorithm gives you some treatment. You probably want a better explanation. You want something beyond computer say so, right? You want to understand what's going to happen to you. So with the rise of deep learning, model interpretability really became a problem, because the more complex is the problem, then more difficult it is to understand how to explain it. And deep learning models are very unfamous for their uninterpretability. There's a lot of things which are inside, many layers, there are a lot of parameters. Yeah, we don't know how to explain. It's a black box. So how do we deal? How do we deal with interpretability in this case? What we usually end up with, we are finding a trade between white box models, which are not so very accurate, but they are really transparent. And there is a black box models, which are really accurate, but absolutely no idea what's inside, and sometimes you don't even know if your algorithm generalized or just learned all examples. So, but there is one approach which is very modern and very promising, and I want to share it. It's called model agnostic interpretation. So we take a step back from developing a machine learning solution, and then I think we insert interpretability as another requirement, as another step during the process. So the first step is the world. That's everything we can observe, everything which is interesting. The second step is data. That's where we digitalize the world. We connect telemetry, we connect pictures, videos, all this. On top of the data, then, we consume the data, we build the models. And then, instead of directly presenting results to user, as we do now, we demand another layer, which will explain the decision to user. So user will get decision and explanation. So for example, why this image said, why classifier said it's a cancer on the image, or why this mail was classified as a spam. So of course, it's a very simplified approach, but I just wanted to tell you to kind of bring explanation of model interpretability, become a new layer in the process of developing machine learning solution. And it's very interesting. So there are, of course, cases when we don't need model interpretability. There's always such cases. For example, MNIST and hand-digit recognition, handwritten digit recognition. There are so many things done about it. Everybody knows how it works. Nobody is interested anymore. Or if I build a toy model which would tell me, let's say, estimate my arrival time to work based on time I wake up. I don't really care what's inside this model. I don't really care if the model takes it wrong. It's not important. Also, there is model interpretability which can backfire on you. For example, if there is an intention to fool the model. If I know how the model works, what's inside, for me it's getting really easy to fool it. If I am a spammer and I want to send mails with spam, and I know that spam filter reacts on certain words, I would just ignore these words. I would not include them in my mail, and hey, I'm in. So as you can see, model interpretability is pros and cons as everything else, but it's getting more and more important in our field, and it's definitely here to stay. Another thing which is, according to my personal opinion, and not only my personal opinion, which is definitely here to stay, is automated machine learning. Well, automated machine learning, as a term, became mainstream in 2017 when Google Research published Google's AutoML. They introduced a machine learning approach to define and train models, because traditionally those tasks were beyond abilities of non-experts, so Google made it possible for non-experts to do it. And ever since, when people speak about automated machine learning, what they mean is model selection and training. But traditionally, automated machine learning is way beyond that. It's about automating the whole process of applying machine learning solution to the world. It can include data processing, feature engineering, extraction. It can be model, of course, selection and tuning. It can be monitoring. It can be a lot of steps. But, and of course, as any automation, it provides you such advantages as building robust, sustainable solutions, sometimes even better, not always, but sometimes. And it contains various steps. But the only thing people talk about is model selection and tuning. That's it. And that often brings question, if a data scientist can be replaced, if it's not actually a job anymore. Let's take a look what else we data scientists do. Because building model is just a piece of complex process. Tiny fraction of the code, of your whole code, is actually doing machine learning. Tiny fraction of the time you spend on making a product is actually spent on model tuning and selection, which may come as a surprise, given amount of papers and research and everything in the area. But when it comes to industry, where we are in the industry, where do we really spend effort? Well, first of all, data scientist, as a part of data scientist work, is to identify the area where we can apply machine learning solution. This is hell a lot of analytical work. You have to be a domain expert. You have to understand what you're working on. You have to collect initial data. You have to make some bold assumptions and build proof of concept. Once that one is in place, yeah, it kind of works. The next step is also in data scientist is framing a project. How complicated it is to integrate machine learning approach to existing product. Because it's honestly, really seldom we build something from scratch. We take an existing product and we add machine learning on top of it or inside of it, some piece. Then we have to look at what kind of data organization already has, what kind of data we need to collect, what are the risks, what are costs, what are constraints. This requires architectural mindset, understanding domain, and understanding of existing products which your organization already using. The next step is building data pipelines and data architecture. Well, pipelines are by definition automation, automated way of churning the data. But when it comes to data architecture, this is definitely a task for expert. How to design a data flow which is flexible but extendable? How to deal with load, reliability, availability? Then once some kind of data start finally flowing into your system, we have to define features. We have to make data available for modeling. And finally, we're at the modeling. That's where tools like Google AutoML come in their all glory, because it's a good tool. Well, let's talk a bit more about Google AutoML. They deserve it. When it was announced, Google CEO said, I'm going to read it. Today, designing neural nets is extremely time-intensive and requires an expertise that limits its usage to a smaller community of scientists and engineers. That's why we've created an approach called AutoML, showing that it's possible for neural nets to design neural nets. Idea actually is great. Because remember why we originally start building neural networks? Because we deal with such huge amount of data which is too complex to comprehend in our three-dimensional brains. So we build neural networks. They can deal with complicated things. Eventually, we start needing so complicated neural networks that they are too complex for our three-dimensional brains. Been there, done that, so let's make neural networks, build neural networks. Like, why not? And that's known as Neural Architecture Search, or NAS. So NAS is actually an algorithm which can take your data and find the optimal neural network architecture in order to solve some kind of particular task on that data. And it allows you to build really complex neural networks without any understanding of deep learning. The only thing you would need is labeled data. Of course, since it's neural network designed, it can find really complicated structure such complicated that our brain may be not even possible, not being able to imagine it. But complicated is, or complex is not necessarily better. On the left side of the screen, you see a neural network designed by a human expert. On the right side, it's a neural network designed by NAS. And performance of both systems are exactly the same. And it's actually quite computationally expensive to do neural architecture search. So, some of us, people who work in machine learning domain and data science, actually question if it's really required to build a new neural network architecture for every simple task, for every new simple task. So yes, there are a set of people who are working on designing NAS and working on such tasks, but in practice, most of machine learning practitioners are getting away with transfer learning. And we're going to talk about it later. It's basically applying existing architecture to new tasks. Another tool I have to mention, or I want to mention actually, when it comes to automated machine learning is Azure ML. Somebody familiar with Azure ML in this audience? Wow, okay. Very few people, but basically it's a very simple interface which allows you to build pipelines. And if you don't know, for example, anything about machine learning, but you have a classification task, what you can do, you can drag and drop all the models who can do classification, run the flow, and just choose one to go, the one which is best performing. This is really cool because it doesn't require any knowledge from organization. It's like drag and drop, hey, run, deploy. Actually, deploy one button, it's out, it's working. Of course, you will still have to have a guy who knows how to churn data to actually pipe data in. But building machine learning by itself becoming not a problem anymore. This slows the entrance bar significantly. But if an organization really serious about adapting machine learning, and most of organizations are, obviously, hiring data scientists still is inevitable because it allows you to achieve great results and not just some okayish results. So automated machine learning can be applied in plenty of spaces. And there is no single way, there is no silver bullet, no like tool set which we say, this is the one to use, go use it. So we end up with data scientists also selecting tools for automation and doing the automation itself. Which brings me to a question to this audience. For those of you who has been in software engineering for a while, does it ring a bell? A task which exists in every single project, which cries for automation, and every single project or a team find their own way of solving it. Any ideas? Look back like 20, 10 years ago, 15. Remember how we used to build projects? First, it was dev machine. Then we have build machines. Then we have continuous integration and tools, plenty of tools on the market, and you just pick one and you torture it for a period of while, and yes, you have continuous integration build. Then comes advanced tool sets, and they streamline the process. Well, 15 years ago, it would take me some hours to set up continuous integration. Now I can do it in 2-3 minutes. The exactly same thing, and now we, even better, like I'm looking at the slide, we have DevOps, we have continuous delivery. 15 years is quite a journey. Exactly same thing is happening in machine learning field. We do it a lot of automation manually. Now we're streamlining it because tools are getting more available. So it took us 15 years to get to DevOps. Let's hope it will take us less to get to data and MLOps. And that's all I wanted to say about automated machine learning.
And I'm going to talk about the next hot topic in machine learning, transfer learning. So most people are able to transfer knowledge across tasks. When we learn how to solve one problem, we use that knowledge to solve some related problems. For instance, if you know how to ride a bicycle, presumably it becomes easier, at least in my world, to learn how to ride a motorbike. Remember when you learned your first programming language, it took you somewhat less time to learn the second one? So the transfer learning has the same idea. It's a machine learning method in which a model developed for one task is reused as the starting point for another one. So let's say you have a model predicting whether a given picture has a cat on it. If you suddenly need to start predicting dogs instead of cats, you need to build a new model completely from scratch. And normally this requires a substantial amount of time and resources. And it becomes costly to develop new models with the production level performance. Meanwhile, both cats and dogs have some similar features. And there should be a way somehow to leverage that knowledge within the existing model rather than reinventing the wheel, so to say. That's where transfer learning comes in handy. The key idea here is rather than training a new model completely from scratch, you make a much faster progress if you download the weights that someone else has already trained and use them as pre-training for your own neural network. Let's look at a concrete example. Let's say you want to build a model to identify pictures with Norwegian moose.
Not Canadian moose, Norwegian moose.
Yes, this is very important, especially here. So anyway, but of course there are no publicly available algorithms that do this exact job. And training from scratch would take several days, if not weeks. But if you use pre-trained weights, it might be reduced to a day or just a few hours. So with transfer learning, you start with some existing neural network and you tweak it to learn with moose data. First, you would replace the original output layer with your own for moose prediction. Then you gather whatever data set of moose pictures you manage to find and you start training. Another very well-known trick is to freeze the weights in some layers and train just the ones associated with your output layer. This can reduce the training time even further. So, in general, computer vision is one of the areas where transfer learning is thriving. And computer vision research community has been posting lots of their pre-trained deep models together with datasets online so that anyone can easily obtain them. And this is this is meant to scare you. At least I got such feedback that it's a scary picture. But that's just to illustrate some of the pre-trained networks that are used sometimes. So, and as Andrew NG points out, transfer learning will be the next big thing in machine learning in the industry.
I have a question, actually, out of curiosity, pure curiosity. Who knows who is Andrew Ng? Thank you. It was a pure curiosity question. Speaking about next big thing, we are at my favorite part of talk. Spoiler alert. It's about generative adversarial network. Because lately there's been a huge rise of interest into generative models. And those are models which can look at your data and can create examples of the data which are looking similar to the ones they have seen. So they can learn internal representation of the data. And at that point, you probably means like, what? Let me explain. Let's say we have those samples of the data. Pretty simple. If I ask neural network to learn some representation, eventually it will figure out that all the data points are in fact around parabola. And then I say, OK, fine. Show me what you have learned. And it will generate me the data, the points, which are perfectly fit into parabola. And the question is, does this look any like the original examples I had? It's like, absolutely not even close. And that's why generating data is so hard. It's hard to make realistically looking samples. So one of ways to solve the issue was suggested in 2014 by Ian Goodfellow. And since then, it was addressed like the most interesting idea of last 10 years and the most important new development in deep learning. What he came up with was GAN, Generative Adversarial Network. Idea is simple and brilliant. Let's take two networks, put them against each other, and give one of them task to generate the data, and another one task to figure out if data is generated or real. And then run them in parallel, make them compete, and try to beat each other. So this is a GAN architecture. So discriminator is a typical classifier network. As a cat or dog, this is discriminator. To predict a label or a class. This is a very well-known task. It's solved successfully in many, many domains. It's not so interesting. What's interesting is generator, because it has to generate unique and looking like real example. So generator tells if the data is real or not, and generator, or discriminator. And generator takes some random noise and try to produce data samples out of it. What generator eventually does, it tries to fool discriminator. In a real-world sample, very popular way to explain it, imagine you have a guy who wants to fake Picasso. And there is an expert who can actually tell the difference. So as experts become better and better, if see an image is a real Picasso or some bullshit, then the generator or the expert has to become much, or the forger has to become better and better into faking, because or else how can he sell his shit? No way. So that's the same. So generator is the forger, and discriminator is the expert. So when we connect two networks against each other, what discriminator does, it learns data representation or boundaries between classes, and generator has to exploit it. Ideally, in the end of training, generator is so good in generating the data that discriminator cannot see the difference. The question is, why do we care? What's the application of GANs? Well, first of all, many people see GANs being very good into, or promising, into holy grail of machine learning, unsupervised learning, when you just throw a bunch of unlabeled data and model figures something out itself. On a more practical way, the most prominent application of GANs is data augmentation. Imagine you need to train a model and you don't have enough data. I don't know, what you can do, it's not enough. You need like at least 100,000 images, for example, to train a neural network from scratch, and you have maybe 1,000. What you can do, you can generate data you miss. If you think about autonomous driving, how do we humans learn not to crash while actually never experiencing a crash before? If we tell model to just observe what is safe driving, how will the model learn behavior in a critical situation? Or do you really want to crash your vehicle a million times in order to model to get the point? Well, I guess not. So we generate these samples. GANs can also do conversion of day to night or summer to winter, which gives us a possibility to generate those images we are lacking. Like, for example, image with a pedestrian in the night on a deserted forest road in the winter. Unless you live in Norway, there is not so many chances to collect such pictures. Well, another application of GAN is an image reconstruction. It can sharpen your image and make a better quality. It can remove objects and fill the background. It can color images. Well, actually, most of GAN's applications have been around images. Another one is image-to-image transition. You can take a picture, a photo, and make it look like a favorite artist. GANs can also generate music. There has been research papers showing that they can generate music in a particular style you like. Not so very melodic, so I will not make you listen to them, but it can definitely be used to inspire human composers. This is a huge, interesting thing. Another art example, artificial intelligence generate modern art. This is from article from newspaper, a headline. This picture, portrait of Edmond de Bellamy, was sold for $432,000 at Christie's in New York. What's interesting, this picture was actually generated by GAN. GAN trained on 15,000 images on a portrait which were painted between 14th and 20th century. Once the picture was generated, it was printed on ink on canvas, and it's a part of 11 fictional portraits of Bellamy family. Bellamy because it was called after inventor of GAN, which is Ian Goodfellow, and Goodfellow to French can translate as Bellamy. It was sold at Christie's in New York, and making Christie's actually the first ever auction house to put an AI-generated art under the hammer. And some people say this marks an arrival of artificial art to the artificial intelligence to the art stage. If some of you now think, okay, I'm in the wrong business, I'm just gonna drop it all and I go train GANs and I sold pictures. The creator of the GAN didn't get anything because the network itself was taken from open source. So it's not that easy. Another thing, GAN can be used for fun. Fun we like. Look at those people, look at those faces. None of this person exist. These all persons generated by GANs. If you want to see more, you need to go to a site which is called thispersondoesn'texist.com. What kind of feeling do you have when you look at these pictures? Does it make you feel slightly uncomfortable, maybe? Yeah. A bit worrying? Have a look at next picture. GANs have been used to create so-called adversarial attacks. It's when you take a picture and you make a small change to it, invisible to human eye, but totally messing up classification network. So picture on the right, network says 88% sure it's a tabby cat. After adversarial perturbation, network is like 99% sure it's guacamole. You don't argue with neural network. So I think it's funny. What if this network would be responsible for facial recognition of the part of your security routines? Not so funny anymore. Look at next picture. What if I tell you a group of researchers managed to put a sticker on a stop sign and make model believe that it's a speed limit sign? How comfortable would you feel in your self-driving car after that? Maybe not so good. The potential danger of adversarial attacks can be only limited by the imagination of attacker. At this point, you probably wonder if there is any defense. There is no defense. Not of yet. It's a very active research area. Some people suggest to include adversarial attacks as a part of training routine, but really we don't know how to deal with that yet. So as any great invention, GANs can be used and they can be misused. But what I can definitely tell, it's a very interesting area to follow. Another interesting area, I guess.
Yeah, deep reinforcement learning. So in general, reinforcement learning refers to goal-oriented algorithms that learn by trial and error. And the most important thing is that rewards or punishments are delayed in time. That's what makes it difficult. So in supervised learning, an algorithm generally is given a correct label or correct answer for every training example. However, there are many decision-making problems in which this type of explicit feedback is very hard to provide. For instance, if you're programming a robot to walk, there is no correct label to associate with the action of walking. What you can do instead is provide an algorithm a reward function that would indicate when it's doing well and when it's doing poorly. So in reinforcement learning, an agent tries to come up with the best action given the state to maximize the reward. And the agent or the algorithm learns through this state action pairs, and it accumulates them throughout training. And soon the space becomes very large, and it becomes infeasible to store all state action pairs and rewards. We need to use something that can generalize the knowledge, like a neural network that could predict the reward for a given state action pair. So deep reinforcement learning starts when deep neural network is used as an agent that learns to map state action pairs to rewards. For instance, a convolutional neural network could be used to recognize an agent's state, what's in front of them, like a cat in the picture. So they would do the typical task of image recognition. However, in reinforcement learning, they would derive different interpretation from an image as compared to supervised learning. For instance, here, the convolutional neural network could rank the actions that could be taken in a particular state, like attacking a mouse would return 3 points, and waiting for it to come forward would return 5 points.
Or 10, if the big mouse. Big mouse, 10 points.
Yeah. For instance, reinforcement algorithms that incorporate deep learning can be applied to games. And I think pretty much everyone heard of AlphaGo, and that it about how it beat the best player in Azure.
Lee Sedol.
Yeah, I was trying to mispronouncing the name. But actually, in fact, AlphaGo victory had an interesting side effect. If you're following research papers in the recent years, China has been investing a lot of research talent, money, and resources they have to boost their AI field, so to say, because they couldn't believe that some foreign AI company could just suddenly beat the best player in Azure. Deep reinforcement learning can be applied to problems that were previously intractable, like learning to play video games directly from pixels. It could also be applied to robotics, self-driving cars, managing resources in computer clusters, and even chemistry to optimize chemical reactions. And just recently, by the way, Google announced that they have given up their entire control over their data center cooling to one of their algorithms that uses reinforcement learning, and that has previously led to energy savings of 40%. So, as you might have noticed, deep reinforcement learning is surrounded by mountains and mountains of hype, and for good reasons. However, when it comes to final performance, many problems are still better solved by other methods. For instance, this robot by Boston Dynamics doesn't use any reinforcement learning at all. Nevertheless, deep reinforcement learning is expected to revolutionize the field of AI, and it's definitely a step towards building fully autonomous artificial intelligence systems.
Yeah, speaking of that, there's a saying I really like, and it stands like, if it works, it's engineering. If it doesn't work, it's artificial intelligence. I like it so much because it's a precise way of saying where we are right now. Because the route from machine learning to artificial intelligence remains still uncharted. The term AI has been so general and so often used around that I feel like we need to take a step back and remind ourselves what we were originally meant by artificial intelligence and what do you mean when we say this term now. Because most of things which we call for artificial intelligence nowadays are actually used to be called machine learning. Because machine learning is a joint field of statistics and computer science, with the primary goal to collect the data and learn from data how to perform a specific task. And this has been popular for many years already, not just the last decade. Of course, as the amount of data has massively grown and got a lot of computational resources, the term of data science actually shaped out to underline the need in industry to have such experts who can put together data, machine learning algorithm, and make production quality systems. And on the hype of those successes of such systems, people start calling machine learning for artificial intelligence. But originally, artificial intelligence appeared in 1950 to define a software-hardware entity which would possess a human-level intelligence. This is a cover story from Time magazine, which was foreseeing arrival of artificial intelligence, an entity which would seem one of us, at least by mental abilities. This would focus on cognitive abilities of us humans to make a logical conclusion and do reasoning, and generally think of things, not just do something. And it's 2019 now, and remaining thinking is still elusive for machines. What's called AI nowadays is mostly achievement in engineering field. Because if you think of it, a lot of progress has been made by great companies, that's not a question. But does it bring us any closer to true artificial intelligence? Popular fields like natural language processing, search, image recognition, face recognition, fraud detection, you name it. Really cool, no question of that. But the most celebrated successes was in a field which is associated with human intelligence. But if you think of what they do, like associated means like image recognition, speech recognition, gameplay, this is kind of almost like associated with us humans. But if you think what was system do, they collected data and they trained a model to perform one particularly narrow defined human skill, one. Does not bring us any closer to thinking or reasoning. There is also IoT, Internet of Things, very, very hype as well. And what's this about? This is about putting things into internet, making stream their data, become available, and there is no visible development into addressing such things as, okay, how can those things discover surrounding? How can they start interacting to each other? How can analyze each other behavior? How can they interact to human? Because as soon as we put something into internet, we face big problems like security, privacy, and maybe we just so far focus to concentrate on those rather than addressing a definitely bigger challenge of making things intelligent. So, on the hype of technological revolution, are we getting lost on our way to true artificial intelligence? the consequence of misusing the term AI for what it is not is that we actually forgot what we were aiming for. But if we take a step back again and think about all the systems which we call for artificial intelligence now, what are the common fundamental issues which are still unresolved? Well, the first one is adaptability. Most of our systems nowadays, they are getting lost in the presence of new circumstances. They don't know how to behave, then they see signals they haven't seen before or haven't been trained for. There are, of course, fields trying to address it, and transfer learning, which we talked about, is one of them. Then the next thing is also we talked about, it's interpretability. Most of advanced machine learning models do not explain their reasoning, and users don't trust things which cannot explain themselves. The third challenge is slightly different, and that's to understand difference between correlation and causation. For example, there is a high statistical association in a chocolate consumption and the chances to win a Nobel Prize. So statistically, that implies that the more chocolate we eat, then more likely we are to win Nobel Prize. In reality, of course, that would make us fat and not bring any closer to Nobel Prize winning. But what did we actually miss here? Well, the relation between chocolate consumption and Nobel Prize winning is only associative, it's not causal. Another example, in Germany there are regions which have a high positive correlation between stork population and baby deliveries. And of course, it doesn't mean that stork actually bring you babies. And we understand that because we are human, we know such thing. Because we know it should not be interpreted as causal. But how do we explain it to machines? How do we explain that associations driven from statistical observations are not enough in order to build the world picture of the world? There is no way to put in mathematics a simple fact that if storm coming in, the barometer goes down, and not the other way around. There is no way to put in mathematics nowadays that if A causes B, that doesn't mean that B causes A. There are frameworks developing for it, but it's not really finished yet. So the human ability to connect cause with effect is actually a necessary ingredient to achieve human-level intelligence. If we would explain machines cause-effect connection, that would allow them to build a representation of environment. And if they manage to build such a representation, they can start asking questions like, what if? What if I do this and that? It's like interventional questions or retrospective questions like, what if I have done this or that? And such questions, unfortunately, cannot be put or answered by machines or models which we build with statistics and which operate only in statistical space. We need to teach machines to operate with causal relationships. And that's what causal learning is about. So instead of correlating that influenza and fever together, you need to reason that influenza actually causes fever. So it's a very new science. There are a lot of papers this year. There are a few last year. So it looks like exponential development. And the science is developing. It's very young. But I think if we do want to achieve artificial intelligence, I'm not sure we do, but if we do want, this actually might be our best chance. So that's our last topic we wanted to cover. And if you find any of those topics interesting, I hope you liked our talk. And as I said, if you have any feedback, please come and share it with us. Thank you very much.